This lecture series and the content of lectures are designed to be easily understood by everyone, from the curious part-time scientist to the tenured theorist or professor. Each episode will begin with pre-written material, followed by an informal commentary section without notes to draw a conversational style close to the material presented to answer what I think will be anticipated questions to what I have said. We will be building an entire mathematical structure from scratch, literally. I was born a linguistical prodigy that was simply never identified within the educational system. Simply put, I demonstrably understand any logic the first time it is properly explained to me and can learn anything to complete mastery without guidance. From hearing conversational style English, I noticed logical inconsistencies in analytical arguments immediately and at a fundamental level. Consequently, I was conducting independent mathematical research by the age of 9 and conducting research in all areas of natural science by the age of 15. More specifically, when I say doing independent research, I mean directly resolving large-scale theoretical conundrums with new, self-discovered insight, not simply mastering a known discipline such as differential geometry. I graduated high school valedictorian in 2012 and entered Michigan State University with 42 credits from AP Test as a double major in astrophysics and mathematics. After a year of study at MSU, I transferred to Ohio State University and continued in their physics and math program for 3 semesters. While carrying a 3.7 GPA and having completed 112 credits of 120 required to graduate, I approached the administration of Ohio State University with a very direct letter which expressed my inability to learn in the physics program because of errors in the material presented as well as the structure of the classes. I was completely ignored by the administration. In the letter, which is also linked to the website under the Essays tab, I directly described how math and science research is substantially different than undergraduate class structure, which every research professor is well aware of, but no one seems to care about in any practical way. Universities are built for the academic, not the student, and it is apparent. I emphasized that what I was expressing to the administration was not that I don't get this material, but this material is logically incorrect, which it was then and still is right now. You simply cannot accurately test students' knowledge with improperly posed questions, especially in fundamental science. Furthermore, a teacher's ability to test is limited by his or her own competence and knowledge. If no one knows what the foundations of mathematics are, how can a teacher test on a percentage basis how much of math a student knows? You can't. Additionally, science teachers are hardly immune from power politics and career ambitions, which are all extremely prevalent at major universities. The reality of what scientific research is contrasts slightly with how it is portrayed to be. Science is black and white only in time. There are thousands and thousands of new publications every day, so how do you know which ones really matter? Simple. The only theory and the only results that matters are the ones with real, tangible application. While many theorists idealize quote-unquote beauty and elegance, the reality is we need mathematical models that fit the messiness of the everyday world we interact with. Let me be clear. I'm not saying I know all of the answers, far from it. I'm saying I have definitively shown incontrovertible errors present in current theoretical models. When you go into Physics 101, you learn Newtonian mechanics. Albert Einstein's work directly predicates on the work of Newton and is the presiding physical theory of our day. Newtonian mechanics, and subsequently all of fundamental physics, does not integrate friction properly into the logical framework, and friction is the one thing literally required for movement. As a result, entire principles of thermodynamic law are profoundly underdeveloped or completely misunderstood by theorists and by the academic community as a whole. Developing theoretical physics is like building a house. Without properly laid foundations, the house is built on top is bound to wobble and eventually crumble from structural problems. People have been building houses and living structures for millennia, so building plans for houses are well known. In contrast, developing theoretical physics has no blueprints for construction, especially when considering an intractable open problem. So how do math proofs get discovered, and how does physical theory progress forward at all? The answer is found by looking at the structural problems that exist now in current theory, assessing why those errors exist, and then backtracking the logic and figuring out what went wrong in the first place. Once the errors are identified, new observations taken directly from nature must be accounted for to form new physical principles while remaining consistent with all previous experimental results. The current state of theoretical physics is peculiar. What I mean is this. Quantum mechanics is the foundation of quantum field theory. Quantum field theory is immensely effective and is the second most tested scientific of all time. Literally. However, what remains in physics is conundrums. Namely, how have we described so much at a fundamental level, and yet that diction, that vocabulary, that way of talking about the world feels so distant from our everyday lives? What is needed is consistent logical models to assess the data we already have in a more complete picture that satisfies our common sense intuition. School cannot teach something they do not know, and as evidenced by all of history, no new mathematics has ever been discovered from taking a test on what is already widely understood. Consider the key difference between an undergraduate and graduate class environment versus an academic research environment. In class, you are being tested on your recall of material known by the entire academic community, typically for hundreds of years. And in a research setting, you are trying to discover something new. When a truly novel and fundamental mathematical discovery occurs, how could anyone but the person who made the discovery expect what the solution should be? The answer is obvious. No one could by the nature of what a discovery is. Let me be emphatically clear here. Every good mathematical proof is buttressed on common sense and can be understood by anyone after the fact. But the initial discovery must be novel to the mathematician conducting the research. New ideas are logically required to solve old problems. Very literally, by the time I had been exposed to studying the natural sciences in high school, I had already progressed my own research to the point that the structures presented in class were holistically remedial. While the following analogy may seem a bit goofy, it is rather accurate. Consider that you're going to a party with a friend of a friend named Sean who has just learned an interesting riddle. Sean comes over to your house before the party and he tells you the riddle and you think it over for half an hour or so, at which point you confess you can't figure it out. Sean tells you the answer and you react with the ever classic, "Ah, how did I not see that?" after realizing the solution was simple and obvious all along. After having a couple drinks, you and Sean head on over to the party. Throughout the course of the evening, you hear Sean tell the same riddle over and over and over again. While you appreciate that your friend Sean struggles with conversation starters with the ladies, by the time the party is over, not only is the riddle no longer interesting, no one wants to be around Sean. The structure of high school and undergrad when you are already conducting research is a lot like hearing the riddle at the party over and over and over again. If you learn something in one class and extend that logical concept from chemistry to physics to biology to economics immediately, taking so-called different classes repeatedly is the same as hearing the riddle the 100th time. The solution is painfully obvious and you can see the answer coming from a mile away. It is truly uninsightful and it becomes a complete waste of time. My point with all of this is not to criticize the educational system, but to confidently articulate I have been pointing out the same errors in every science class I have taken since being introduced to the subjects in high school. And by the vice of adolescence, I have never been given an opportunity to discuss my own proofs. Let me stress I am presenting proofs, not ideas, and I will discuss the difference shortly. Simply put, errors won't go away just because you ignore them or don't understand they are there. In theoretical physics, the existence of logical conundrums themselves are in fact the evidence that a principle is not understood, not that the answer is complex. For those who are not privy to mathematical research, there are two ways that research is conducted: problem solving and theory building. Problem solving presents a specific solution to a known problem, and theory building provides logical insight to develop future research through novel proofing techniques. My research is mostly proofing techniques developed through novel insights regarding the origins and formation of language. The breadth of mathematical and scientific research is huge. So how are the important results identified over time? What many mathematicians do not know, let alone the everyday person, is that in the early 1900s, the leading mathematicians of the time really felt they were close to a so-called final theory of math, which simply means they expected to understand the basics of number theory, and subsequently the rest of mathematics in total as a consistent framework. Mathematics as it stands right now, today, has no known foundation, and that is clearly a problem. I want you to think of your favorite teacher or mentor you have had in school or in some other aspect of your life. To be specific, I am saying a favorite instructor who helped you solve a logical problem that you had been stuck on for a while, such as a science or business concept. Ask yourself, what made that person a good teacher or instructor? I'm willing to bet the answer for everyone is universal in sentiment. That is, all good teachers provide simple and intuitive answers that make sense to the person asking the question. Simply put, good answers resonate because they coincide with the intuition we already have and know to be true. A lot of people have light bulb moments, and not a single one has resulted in a more complex explanation of a problem. So how do the light bulb moments themselves relate to each other? Whether you are a mathematician or not, everyone has problems to solve, and everyone uses language to solve them. Consider which came first, language or formal mathematics. There is some to debate on what exactly the word language means, but for now I'm defining language as expression. Language consists of any signal, auditory or otherwise, to transmit information to another person or organism. For example, a caveman saying ooh ah at a hot fire would count as language. To be specific about formal mathematics, I am talking about the development of analysis for full-scale logical proofs, not rudimentary number theory such as counting or tallying a merchant's sales list. The answer is obvious. Language substantially predates the existence of formal mathematics. Evolutionary data suggests language capacity developed roughly 50,000 BCE, and extremely generous dating establishes the earliest mathematical texts at around 5,000 BCE. Because of this simple truth, the relationship between language and mathematics is profound. Consider the following equation. 1 plus 1 equals 2. Now, I guess when you see that equation, you recite it to yourself like a sentence, meaning you think 1 plus 1 equals 2 as opposed to visualizing the symbols. Language and linguistic structure far precede mathematical structure, and both formal mathematics as well as problem solving of any kind requires language. Therefore, language must be the basis of mathematics. And the tremendous implications of that simple fact is what I demonstrate in my dissertation. Earlier I said an idea in mathematics is distinctly different than a proof in mathematics. Let's now establish what exactly a proof is and what exactly pushes a mathematical idea over the brink to become a proof. A mathematical idea becomes a proof when the logic present in an argument points to an inevitable conclusion about a given conjecture or hypothesis. A scientist poses a question about the world around him or her and investigates that hypothesis with an experiment. The more experimental results in favor of the argument, the stronger and more convincing the argument becomes. Once enough data has been analyzed and time has passed, the most convincing arguments become inevitable. The absolute key being the inevitability. Facts of nature exist for people to discover, but the facts have always been there. At any given time, it is our awareness of those facts that forms scientific ignorance. All branches of science generate facts through experimentation. Biologists discover facts, physicists discover facts, chemists discover facts, and so on. Facts of nature are universal, meaning a given experimental result must be consistently returned regardless of which scientist is conducting the experiment. Science is predicated on reliability and consistency of experimental results that are articulated as hypotheses. This then begs a very important question: how do all the hypotheses, conjectures, laws, and established facts of different domains of science relate to one another when they are all expressed with logic articulated through language? As stated in the title, an explanation is not a theory. A theory is a centralized logical framework based on a fundamental theorem to analyze and make predictions. The fundamental theorem of a theory is analogous to the thesis of a paper. It is the main point from which all subsequent results are derived. Many people, including PhD professors and researchers, call explanations theories when in fact there is not logical consistency. Finally, there can only be one true fundamental theory because there is only one environment which every scientist measures from. In December 2016, I circulated direct and explicit experimental predictions regarding thermodynamics and semiconductors titled Vibrational Information Theory. Vibrational information theory is a theory of language which asserts that language is minimalistic and optimal. That is, people construct the simplest linguistic structure to represent the physical objects and actions that they observe and interact with in their environment. As I stated earlier, new physical theory requires new phenomenon, and current theory does not identify rhythm as a fundamental physical phenomenon, which it is. Rhythm dictates the structure of music, rhythm dictates the structure of flow, and rhythm dictates the structure of momentum. To see this immediately, turn on any sports game and watch until you hear the announcer use the word rhythm. Using this logical framework, I predicated I predicted a direct breakdown of the Wiedemann-Franz law, which states that any good conductor of electricity is subsequently a good conductor of heat. The Wiedemann-Franz law has been a sturdy logical underpinning of thermodynamics for well over 125 years. My directly articulated prediction was that timed movement of objects limit the amount of heat dissipated from a system in motion. In the same exact way that talking is different than singing and walking is different than dancing, timed movement establishes rhythm. Verbatim from my thesis, I stated the following: Mrs. Scott, get up and walk across the room. Mrs. Scott, get up and march across the room. March like a tuba player would do in time to music. You might notice that when you march, you almost feel as if you are transitioning your momentum smoother. Consider the walking motion itself. VIT would say that instead of mass accelerated to move through space-time, this is what is happening. The space-time energy wants to vibrate and exchange information in a steady state, walking versus marching. So it begins exchanging information through vibration with itself to discover new steady-state vibrational patterns. In January 2017, 2 months after I had circulated my predictions, vanadium dioxide was found to transmit electricity, but not heat, due to the timed movement of electrons by Jung-Woo Wo and his researchers at the University of California, Berkeley. Since then, numerous experiments have demonstrated that the presence of rhythm is a universal phenomenon in condensed matter. Reading directly from the official press release of the discovery regarding vanadium dioxide, excuse me, this was a totally unexpected finding, said study principal investigator Jung Kiao Wu, a physicist at Berkeley Labs, Materials Sciences Division and UC Berkeley Professor of Materials Science and Engineering. It shows a drastic breakdown of a textbook law that has been known to be robust for conventional conductors. This discovery is of fundamental importance for understanding the basic electronic behavior of novel conductors. In the course of studying vanadium dioxide's properties, Wu and his research team partnered with Oliver Dallaire at DOE's Oak Ridge National Laboratory and an associate professor at Duke University. Using results from simulations and X-ray scattering experiments, the researchers were able to tease out the proportion of thermal conductivity attributable to the vibration of the material's crystal lattice called phonons and the movement of electrons. To their surprise, they found that the thermal conductivity attributed to the electrons is 10 times smaller than that would be expected from the Wiedemann-Franz law. The electrons were moving in unison with each other, much like a fluid, instead of as individual particles like in non-normal metals, said Wu. For electrons, heat is a random motion. Normal metals transport heat efficiently because there are so many different possible microscopic configurations that the individual electrons can jump between. In contrast, the coordinated marching band-like motion of electrons in vanadium dioxide is detrimental to heat transfer, as there are fewer configurations available for the electrons to hop randomly between. Not only did I predict a fundamental breakdown in a robust and well-established thermodynamic law by walking around my living room, I directly predicted the language and specific analogy used in which their discovery was described 2 months before it happened, while being completely oblivious to their research. Since the initial discovery, I've been proving upwards of 20 theorems a day from first principle, which is widely known in the academic community of theorists. What I am presenting is a comprehensive derivation of physical law as a complete body of mathematical work, not an individual result or a handful of results. As of December 2018, I have proven roughly 7,500 theorems. Eric Weinstein, a widely known mathematician and economist who is the managing director of Thiel Capital, that is Peter Thiel, the philanthropist and investor from Silicon Valley, can be seen here discussing my work and the current state of physics research. I have personally derived and resolved every logical conundrum that comes with the question, how do we reconcile general relativity and quantum mechanics? Physics has been stuck for well over 40 years, and that period of stagnation ends today. Take a moment and look around the room. How many dimensions do you live in? I hope you quickly arrived at 3 as the answer. Now ask yourself, has anyone ever lived in a different number of dimensions than you live in right now? That answer is an obvious no. Finally, has anyone ever conducted a measurement of an object or of a system in any other dimension than 3? The answer is also no. So then, How does the fact that people have only ever conducted measurement in 3 dimensions affect the development of language and subsequently the measurements of mathematics and physics? Check out my second lecture to find out. Hey everybody, thanks for checking out the first lecture. The explanation section is mainly for, once we start doing the mathematics, I'll be writing stuff up on the board and explaining stuff a little more and going over evidence and whatnot. But I will put the link to the Eric Weinstein video as well as the link to the Duke study on the credits. Thanks again, and come back for lecture number 2.